So the topic of today is what's cardinality, more importantly cardinality of infinite sets. Okay, so we'll talk about infinities. What is an infinity? Are there more than one infinity, or is just a number, or what is the status of this thing? Okay, so we'll talk about infinity in terms of cardinality of infinite set, okay, which we haven't defined yet. We know it's cardinality of a finite set, but we'll see. Okay, so remember a function. A function from a set x to another set y is a mapping of every element of x to exactly one element of y, the codomain. Okay? A mapping from every element to exactly one element of the codomain is called a function. So, some terminology: domain, codomain, range, image, pre-image, right? All of you know that. So, we are going to we just talked about a couple of representation of functions. One is that bipartite graph. You draw the domain on one side and the codomain set on the other side, and if x is mapped to some element y, then you draw a line between that x and y, right? So, the pre-image and image mapping is there. And then we also saw that we sometimes can describe it with a formula, especially if the domain and codomain or both are infinite, then it becomes very cumbersome to draw, right? Or very large, then it's not easy to draw. So, another representation of function is what's called a list representation, or ordered list representation. Now, we have enough vocabulary when we studied sequences and other things, so we can talk about this. That is just you fix some ordering on the domain. So, let us say x is a domain and there is some ordering x1, x2, x3, x4. You know which is the first element, which is the last element, which is, if it's finite, which is the fifth element, which is the 17th element, and so on. And then you just write in the list form, in an ordered list form, is a sequence of images. Okay. So, the first one you write first thing you write the image of x1, the second you write the image of x2, then f of x3, f of x4, f of x5. That could be a representation of function, right? So, essentially just images listed in the order that was imposed upon x. Okay. So, here is a function. If you remember, that is how we represented it, this bipartite graph thing, and that function can be represented. If I fix this order x1, x2, x3, x4, x5 on the domain, then I can just write a list of 5 f's, and that will represent exactly this mapping. Okay, this mapping. What is f of x1? What is written in the first place? What is f of x5? What is written in the fifth place, right? Here is another function that we discussed earlier. So, again there will be 5 elements in the there will be a 5 length list, and the first one will be the image of x1, the second will be image of x2, and then x3 and x4. Okay, is everybody clear about this representation, this cross representation of different representations of function, right? It's very clear. And when this thing I have written that in a kind of a dimmed font color, because we now going to write it if it is clear from the context. If the set x and the ordering is clear from the context, I'll just give you the list of images, right? So, for example, when we did sequence, we talked about this thing. So, what does this mean? What is this? It's a sequence of squares, right? But if you, so it actually represents this function, right? So, I know this is actually f of 2, where f is this thing. So, but I don't need to write this is second, third, fourth, right? By the placement, I know what is this thing, right? So, that sometime we'll do this, and so this is not our focus point. I just want to develop a vocabulary so I can talk about our main topic of the lecture. So, if I can represent function as a list, then now we want to see how do these properties of functions that we studied, how do they look like in terms of this in the, if the list function is represented as a list. Okay. So, what is a one-to-one function? A function is called one-to-one if two different elements of the domain are mapped to two different elements of the codomain. and that's for all pairs of it, right? So if the pre-images are different, the images must be different. Every image is unique. Nobody shares the image, right? No two elements share an image. No two elements have this common mapping, right? So always think of this thing I told you last time also. Think of the domain is a set of students, codomain is a set of rooms in LUMS hostels, right? A function, a list set of hostelite students if you think of them. So then a function is everybody gets exactly one room. That means nobody sleeps in the street. We are talking about hostelite people only, and nobody gets more than one room, right? So is in a list representation, this room assignment, if it is indeed a function, right, and it seems to be a function, why would anybody gets two room? But suppose that is a function, so then in a list representation it would be just sort or order the student's roll number, the hostelite student's roll number in some way, and then write room number, hostel number, or whatever room ID you have, right? So room number 23 F4, room number 24 M2, or this kind of this will be a list representation of that function. So how would you describe one-to-one function in terms of list representation? What properties must that list have for the function to be one-to-one? There is no repetition in the second column, the images, right? So sometimes it will be just one column or one row, one list, right? We will drop the context, we will drop the domain if it is clear. So no repeated images, right? So a function will be one-to-one if there are no duplicates in the list, if there is no element is deleted in the list, right? So no element in the codomain is repeated. That means no room number is repeated for more than one student, right? For the second student, there is no room number. That means the function is one-to-one. That means everybody gets a unique room. Okay, is this clear? So this way of looking, now I can ask this question, and this is what we saw earlier also. If I have a function from x to y, a mapping from x is the domain, y the codomain. If the function is one-to-one, what can I say about the cardinality of this domain and codomain? Just one second, now don't answer, analyze the question, come up with examples of the question. Suppose somebody said that I did a room assignment for all our slide student to all LUMS rooms, and so the 10 students are assigned room is a function thing, and somebody told you no two share a room. Then what can we say about the number of rooms? The number of students is 10. How many rooms must be there? If no two shares a room, at least 10, right? So in general thing, if x number of students, if x is a set of students, the cardinality of x and everybody got such in a room such a way that no two share a room, then how many rooms must be there? What should be the cardinality of the number of rooms? Why? This is the question. So greater than or equal to x must be less than or equal to, the cardinality of x must be less than or equal to cardinality of y. Does it make sense? Okay, so the cardinality of x must be smaller than, less than or equal to the cardinality of y, okay, if the function is one-to-one. Okay, so an onto function, what is an onto function? It's a mapping from elements of x to elements of y such that every element of y is assigned to at least one element of x, right? So in the hostelite students and room allocation thing, no room is empty, no room is unallotted. Okay. So in the list representation, how would this look like? Every element of y is the image of something, of at least one thing. So in the list, how would it look like? This function, how would it look like in a list representation, an onto function? So if I write x in some fixed order, and on the next column I write images of x. So and I say the function is onto. So in the list, what would I say?
So every element in the y, the image column
That's always true. You will not write anything other than there is a unless it's mapped to something, right? We are just writing images, so they must be assigned to something. So, but that's what was the previous thing in the list. Look, so let's look at this. Is this function onto? Look at this thing. Is this function onto? Why not? No, from the list, how do you know it's not one to one? From the list, how do you know it's not one to one? F is repeated. One to one. Is it one to one? You can't say. You just did the in-class problem 1. That was. How do you know if this function is not one to one? Yeah, but from the list thing, how would you say? Like x3 is not equal to x4. x3 is student 1, x3 is 4 is some other student. Yeah, there are more than one b's. B is repeated, right? A is repeated. Okay, so how would you know if the function is onto, or let's say not onto? If I give you a function, how would it look like in list? Or how do you know it's in the list? How would you figure that this is not an onto function? Or is this function onto? How do you know from the list? Nothing is mapped. Mapping is done from x's to these a, b, c, f or something, right? Assigned, yeah. S is not listed. S is not in the list, right? So f is not assigned to anything. You see, room number f is empty. Okay, it's not allotted to anyone. So this function is not onto because f doesn't appear. Why is it not one to one? Because b appears more than once. Okay, or a appears more than once. So in the list representation, every element of y must appear at least once. At least once. Okay, so, no, it's one to one. Okay, so that was at most once. Here every element of y, there we had to say that every element of y appear at most once, meaning there is no repetition. This thing they gave me, this different thing. So there is no repetition here, right? At most once. And this one says there is no missing. Every element of y must appear at least once. Okay, in the list representation must appear. So now, what can you say if you have a function with cardinality domain x and codomain y, and somebody tells you that the function is onto? What must be the cardinality of x and the cardinality of y? If 5 students were allotted 10 rooms, can somebody claim that I did the allotment in an onto function fashion? If 5 hostile students got, and there are 110 rooms, and there was an allotment as a function, can that function be onto? Why not? At most 5 rooms can be occupied, right? Because it's a mapping, it's a function. Everybody gets exactly one outcome, one room. Okay, nobody gets more than one room. So in generally speaking, if elements of x are mapped to element of y in an onto fashion, what must be the relation between the cardinalities of x and y? No, y is a set, not the range. Range is the actual images. Cardinality of x must be greater than or equal to cardinality of y. That's the correct answer. Why? Because suppose x minus 1 people, elements of x are mapped to some element, y minus 1 elements are mapped. So if let's say cardinality of y is 100, if anything less than 100, let's say 99 or fewer elements are mapped into the 100 rooms, then at least one room will be empty, right? It cannot be an onto function. It cannot be an onto function. So, it must be at least 100 students, maybe 110 students, but then somebody have to share, but then I can claim that the students that all rooms are allotted, right. But other than that, it is a necessary condition, it is not a sufficient condition. Just because the cardinality of x is bigger than cardinality of y does not mean that there will be always an onto function. Function depends on how do you do the mapping, right, but it is a necessary condition, right. If the function is onto, then the cardinality must be like this. Okay, the cardinality of x must be bigger than cardinality of y. Okay, so again I told you the topic of this lecture is cardinality. So, we begin with this just so that we are able to talk about this. What is a one-to-one correspondence or a bijective function? It is a function that is both one-to-one and onto, right. So, in the list representation, the function is one-to-one, meaning every element of y appears at most once in the list. Okay. The function is onto, that means every element of y appears at least once in the list. So, a function is a bijection if it appears both at least once and at most once. What does that mean? Exactly once, right, exactly once. So, a function is onto if every element of x, every element of y appears exactly once in the list representation of that function. Okay. From this, we also just combine it with the two ICPs, we conclude that if there is a bijection from x to y, then the cardinality of x must be equal to the cardinality of y. Why? Because one-to-one is telling us that the cardinality of x is less than equal to cardinality of y. Onto tells us the cardinality of x must be greater than equal to cardinality of y. Combine both of them, the only possibility both of them can be simultaneously true if the cardinality of x is equal to the cardinality of y. Okay? So, whenever there is a bijective function between x and y, then the cardinality of x must be equal to the cardinality of y. Okay? So, that is the relation between bijective function and bijections and functions from with the cardinalities, and this is where we will build upon this. Okay. So, this is a summary of what we did so far. If there is a function from x to y represented as a list, then if the function is one-to-one, the cardinality of x must be less than or equal to cardinality of y. If the function is or every element of y must appear at most once, and if the cardinality if the function is onto, then every element of y must appear at least once in the list, right. And if the cardinality, if the function is a bijection, then every element must appear exactly once, right. All of this thing summarized, this is our take home message. If there is a bijection from x to y or between x and y, then because the inverse function is also a bijection. So, if there is a bijection between x and y, then the cardinality of x is equal to cardinality of y. Okay. All of this was in terms of mainly finite sets. Let us just do this same exercise. Actually, we repeated these questions, but I just want you to write a brief sentence or a brief word about it. Suppose function from a to b and the cardinality of b is bigger than the cardinality of a, right. Can there be a bijective function? Can the function be a bijection? Why not? Sorry? Yeah, why is not cardinality not equal? Huh? Can the function be a bijection? The function cannot be onto. Why it cannot be onto? Which has no pre-images. Yeah. Yeah, okay. So, if you insist that everybody is mapped, then it is actually not a function. Yeah, okay. So, then it will not be a function. Okay. Again, if b is bigger than a, if the number of rooms is more than the number of students, then it cannot be the case that all rooms are occupied, unless somebody got more than one room, which means it is not a function. Okay. So, the function cannot be onto, and the function is not onto, it cannot be a bijection. Okay. So, the reason which you ought to write is that okay, such a function in this, for this b and a, no function can be an onto function. Okay. if anything, any f, any mapping that is a function cannot be onto. Okay. So, if there is a function between a and b and the cardinality of a is less than the cardinality of b, then can the function be a bijection? Cardinality of a is bigger than the cardinality, so cardinality of b is less than the cardinality of a. So, can the function be a bijection? Right? If more number of students go to fewer number of rooms, then somebody must share rooms, right? That means the function cannot be one to one. The function not one to one meaning the function cannot be a bijection. Okay. Now, if we have a function and then the cardinality of b is equal to a, then can the function be a bijection, or would this function be a bijection? Would it always be a bijection? So, that is what it says. Does f have to be a bijection? What's the cardinality of a here? And what's the cardinality of b? Now I have a function. Is this a bijection? Why it's not a bijection, by the way? It's not what? Is it one to one? Yeah, so it's not one to one, it's not onto, it's not a bijection. This question says here's a function from a to b, and now it just happened that the cardinality of a is equal to cardinality of b, right? Doesn't mean the function, any function will be a bijection. It just says that there could be a bijection. If there is a bijection, then the cardinality must be equal. If the cardinality is equal, doesn't mean that every function will be a bijection, right? Bijection can be made, but not every function. Okay. Remember cardinality of finite set. We talked about there also when we talked about sets, I mentioned the word finite, keep that in mind. Cardinality of finite set is the number of distinct elements of x, right? It's a number, okay? It's a cardinal number, it's a counting number, okay? It can be an answer to a counting question, a positive, non-negative integer, etc. Now, we know when do x and y have the same cardinality? If they have exactly the same number of elements, right? So, we also know that if there is x and y is a bijection and x and y are finite set, then cardinality of x is equal to cardinality of y. That is what we saw there, right? If there is a bijection, then the cardinality must be equal to the domain cardinality must be equal to the codomain's cardinality for finite domains and codomains. Okay. So, for finite sets x, if the cardinality is equal, then there is a bijection between x and y. This is slightly different statement, right? There I gave you a function and I asked whether it's a bijection or not a bijection, right? So, we don't know when it will be a bijection. We just saw the last question that not every function is supposed to be a bijection, right? Here this says if the cardinality of x is equal to the cardinality of y for two finite sets x and y, then there exists a bijection. Then I can somehow construct a bijection between them, maybe more than one, but at least one bijection exists. Does it make sense? Okay. So, if you really think about it, so this is if and only if statement. If there is a bijection, then cardinalities are equal. We know that, right? We discussed that. Now, if the cardinalities are equal, can I always construct a bijection? Why not? I can always construct a bijection. No, we established that thing that if the cardinalities are equal, doesn't mean that every function between them is a bijection. This one says that there exists a bijection. Okay, so what I was saying is this thing: if x and y have the same cardinality, then I can construct a bijection between them. Does it make sense? Bijection. The bijection is a property of a given function. You give me a function and I will tell you whether it's a bijection or not. Here I am saying I can construct a function that will be a bijection if the cardinalities are equal. If you really think about it, This is exactly how we do counting. So, let me just give you in formal proof. Formal proof is, okay, let us fix some ordering of x. X is a finite set, right? I can fix an order. This is the first one, this is the second one, this is the third one. Any arbitrary ordering will work. Okay? And then and some order, some ordering, or exactly the same ordering for y also. So, essentially you write x and y on top of each other, right? And that is the bijection. I am saying, okay, the 19th x element is mapped to the 19th y element. The 74th x element is mapped to the 74th y element, right? So, fix any ordering on x and y, and f of xi, the ith element, is mapped to the ith element of y. This is the function. This function is a bijection. Just one second. I don't like words, fancy and difficult words. I get scared of them. I told you long ago. Don't scare me. Does that make sense? I have two sets, x and y, two properties of them. Both of them are finite. Second is their cardinalities are equal. Okay, their cardinalities are equal. I am claiming there exists a bijection between them, and I am going to prove it to you by a constructive proof, a direct proof, right? If the cardinalities are equal, so what this says is write x in some ordering and write y below it in some ordering in another array, right? And the ith element is now mapped to the ith element of y. Ith element of x is mapped to that, and that's a bijection. Is it a bijection? Can some element of y be missing? Can some element of y be not assigned to any x? Why not? Where is the 17th y 17? Who is this assigned to? F of x 17 is equal to y 17, right? So, any x, any yi, I can say it's the image of something, right? Can two x's have the same image? Could it happen that f of x 17 is equal to f of x 3? No, because f of x 3 is mapped to y 3 and f of x 17 is mapped to y 17. They are different, right? So, it's a one-to-one function and so on to function, and that gives me a bijection between x and y. What did I use? Their finiteness and their same cardinality, right? Same. So, and that's how we do actually do counting. When you really say, when I tell you there are 14 people here and 14 people there, in our brain we actually establish this bijection between them. We always do counterpart thing, right? So, okay, so how do I know that? So, let's see, how many elements are there in the set x and y? What's the cardinality of x? 3. And what's the cardinality of y? How do you know these cardinalities are equal? Are they equal?
Yes.
Oh, how do you know?
Because each mapping of x is one mapping of y.
Yeah, so I can make a mapping between them. I can make such a mapping that if there is a bijective mapping between them. So, in our mind now we know, we do it so fast that we don't notice it. We know, okay, 3 is equal to 3, so that's why they are equal, right? But in our mind, why is 3 equal to 3? If I ask you why is 3 equal to 3, this is how we are going to prove it. Okay, so there is the first thing, apple. Let's say for this cross counting, you know, this counting games, right? When people do these so when people do, just to, if I tell you I have 5 rupees and you have 5 rupees, why are they equal? For every rupee you have, I have a rupee, and vice versa. That's how we know 5 is equal to 5. Okay, so the reason we know this cardinality of x is equal to cardinality of y, because I say, okay, for apple I will count A, for 20 I will count B, and for banana I will count C. And that's why these two are equal. Nothing is remaining there in x, nothing is missing in y. For everybody I have a corresponding thing, right? And that's a one-to-one correspondence. Okay, for every element of x there is a counterpart, a unique counterpart, and for every element of y there is a unique counterpart in x. That establishes that these two have the same cardinality. Yes?
So will it have more than one bijective functions if the cardinalities are equal?
Could be many. Could be many. Actually, that's what one of the counting questions. There will be exactly, in this case 3 factorial, there will be n factorial cardinalities bijection when they have both have n elements. It's a definition of permutation. Okay. So the next one is 5 elements in x, 5 elements in y. How do I know they are equal? Well, I can convince you they are equal, because for 1 I will cross out a, for b I would cross out 2, or the other way around. For 3 I will cross out c, and for 4 I will counterpart cross out the d, and for 5 and I can do it in many different ways, right? But for 1 to 1 I have to do this 1 to 1 correspondence, right, in both directions. So that's why the word 1 to 1 correspondence come from. So we know that if two things, if x and y have the same cardinality, if and only if there exists a bijective function between f and x and y. Okay. Now let us just do a little bit more. This is an example. You are going to work with this. Help me with this. Suppose I have a set A, and it has n elements. How many subsets does A have? How many subsets are there for of set A who has n cardinality?
So
2 raised to the power n, right? How many bit strings are there of length n? How many different strings, how many different numbers can you express in n bits? What was the length of the truth table which has two variable? 4, right? 2 to the 2, right? That's 0, 0, 0, 1, 1, 0 and 1, 1, right? How many bit strings are there of length n? How many bit strings of length 1 are there? How many bit strings of length 1? 2, right? 0 and 1. How many bit strings of length 2? 4, right? 0, 0, 1, 0, 0, 1 and 1, 1. How many bit strings of length 5? 2 raised to the power 5, right? So in general, how many bit strings of length n? 2 raised to the power n. Okay. What is this thing? I ask you how many subsets does a n set have? You said 2 to the n. Then I asked a very different question, how many bit strings of length n are there? The answer was 2 to the n, right? So what happens is the set of bit strings of length n has the same cardinality as the cardinality of the power set of A. Okay. So these two have the same cardinality. By the theorem, there must be a bijection between them. So let's try to see if we can construct a bijection. Okay. So how many bit strings of length n are there? How many n bit strings are there? N bits strings, 2 raised to the power n, right? How many subsets of A are there? What's the cardinality of the power set of A? 2 raised to the power n, right? So I got two sets whose cardinalities are equal. Let's see if I can demonstrate the theorem. The theorem said two sets have the same cardinality. We must be able to make up. There must exist a construction between there must exist a bijection between these two sets. Okay. Can you see a bijection between them? Can you design a bijection between this A and this power set of A and the number of in the set of bits, all bit strings of length n? What is the bijection?
Again, you could give them any ordering, and then you would just have to map from x1, f of x1 is equals to y1.
No, what is y1? What is it? Okay, so let's say A has A1, A2, A3 up to An elements. So he suggested fix some ordering of A. Okay, fix some ordering of A. Now each subset of A is now written in some particular order, and we know there are 2 to the n of them. Now what is the bijection for the bit string? What is the order of the bit strings, or in what order are you writing that set of all bit strings of length n?
Just provide the same indexing again. And
Same indexing what? No, there is no indexing there. No?
For example,
So string is given to you.
I don't know what a bit string is. So
Bit string is a 0 1 string. It's a 0 1 string. It's written there, bit vector representation of sets. Recall that thing. Characteristic vector representation, attendance register representation of a set. Yes.
So we can go in descending order from all zeros to all ones.
Random, like we did before,
What is random?
in any
Yeah.
order.
We can assign every element we want to be mapped on the other set. हम चाहते हैं कि this element in set A.
Not set A, the power set of A.
The power set of A will be mapped onto that element of
Okay, so give me
bit
that.
string.
Yeah, bit
And
string.
we arrange that in that particular order.
So, give me that indexing.
So the first element of power set will be mapped to the first element of.
So, what is the first element? Now, you have to give me the first element. You didn't give me any ordering of, give me ordering of A. We didn't do any ordering of the power set of A.
वो तो depend करता है हम क्या function बनाना चाहते हैं.
Sir,
तो हाँ बनाओ ना.
can we do it like this, that if our bit string is all zeros, we map it to the null element of the power set?
Empty
And then-
set.
Empty set, sorry. Then we have like 0, 0, 0, 1 somewhere, and then we map it to the element in the power set which has the cardinality.
Yeah, that's exactly. See, when we did set theory, we had a whole section of this thing, bit vector representation of set, right? So, you in each bit, the first bit correspond to the first element of A, because that is why we fix an ordering of A. The 19th bit correspond to the 19th element of A. And now, if that is 1, that means this subset, the subset being represented by this bit vector, this subset means this subset has the 19th element of A. And if it is 0, that means the 19th element of A is not there in the set. Okay? So, I don't want to go to, but you cannot forget stuff like this. These are so fundamental. And where is sets? When did we do sets? Remember this thing, right? So, this set has 1, 2, 3, 4, 5, 6 elements. I like the 6 length strings, 6 length bit strings, right, or 6 bit strings. And now 1 means this is a subset. It will be there in the power set of these 6 elements, right? So, this subset can be represented by this bit string. This subset can be represented by this substring. How many ones will be there? How many zeros will be there? How would you represent the empty set? How would you represent? Actually, we talked about that one-to-one correspondence between them. Any subset of n bits n set can be represented by n bit vector. Okay, n bit vectors called, it is actually called the characteristic vector, or it's called the attendance register vector of the set, right? Who's there, who is not there is represented by the bit value 0 or 1. Okay, so this is the bijection between them. Yes. Okay, so we saw this thing that for finite set, okay, if the cardinalities are equal, then if and only if there is a bijection between them. Okay, so here is a set X, he says 6 elements, set Y it has 5 elements. There is, the theorem says the cardinalities are not equal. According to this theorem, we must not be able to make, there must not exist any bijection between them. Okay, so can there be a bijection between them? Suppose I have some function from this set X to this set Y. Can that function be a bijection?
No.
Why not?
There will be repetition of the list.
Yeah, if you represent it as a list, so because there are 6 elements are mapped into 5 elements, or 6 people went to 5 rooms, at least 2 must share a room. Yes, cannot happen. Otherwise, if everybody is going to a unique room, then one of these idiots will, at least one of them will stay on the street, right? They will not get no room because there are only 5 rooms. Okay, so there cannot be a one-to-one function between them, and hence there cannot be a bijection between them. Here is another one. It is set X exactly the same, 5 elements. Set Y has 7 elements. Can there be a bijection from X to Y? Can there be a bijection from X to Y? Why not?
There will be some element in Y that does not have a pre-image.
Yeah, so there must be an element of Y which does not have a pre-image. Why must there be an element, such an element of Y?
Otherwise, it would.
The cardinality of Y greater than the cardinality of X.
Yes, that's, I gave you that, but why must there cannot be in any mapping, some element of Y must be not assigned to anything?
Because then some X would have 2 images.
Yeah,
which
if
are-
suppose all these 7 elements of the codomain are actually images of something. Now, because there are at most 6 pre-images, 7 images, 6 pre-images, meaning somebody got 2 rooms, right? If 6 people went to 7 rooms, and all rooms are occupied, that means somebody got 2 rooms, right? So that function cannot be onto. That means the function cannot be a bijection. Okay, so that's the relationship between bijection and cardinalities in checking the cardinalities of 2 things for finite sets, right? So let's extend this whole discussion to infinite sets. What happens to infinite sets? So this is what we discussed. Okay, let's talk about some infinite sets. Z plus, the set of positive integers, right? And Z negative minus is the set of negative integers. Okay, I have listed both of them and I have given description of both of them. I am asking you which one of these 2 is bigger set, which one of 2 has bigger cardinality. We haven't defined as such the cardinality of an element of an infinite set, but cardinality of an infinite set is, let's say, the number of elements in it, right? Which one of them has more elements? They are equal. Okay, so let's say there is a set of positive odd integers and the set of positive even integers, right? Examples are given here. Which one of them have more elements? So O and E, the cardinality of O seems to be equal to the cardinality of E, right? Yes? Okay, let's go make it more interesting. E is a set of even numbers, is even positive integers, and N is a set of natural numbers, right? You can count 0 or 1 or wherever you start from. So positive, so a set of natural number is now 1, 2, 3, 4, 5, 6. Which one of them have more elements? N has more elements. Why? Why does N have more elements? E is a subset of N, right? The number. Yes. Why?
For every element of E, there are 2 elements.
No. Yes, that's not easy answer. Easy. Yeah, N has, in addition to E is a subset of N. In addition to E, N has also odd positive integers, right? So E seems to be have fewer elements. So N now even more sparse set of perfect squares, right? So even was skipping 1 and getting every other natural number was included in E. Now a set of perfect square has only squares included, right? So the 10th square is 100, right? So I skipped 90 numbers in the 10 steps. I skipped 90 number out of the first 100 and only collected 10 out of them, only 10 out of them, right? So which one has more elements? Natural number has more elements because it has non-squares also, right? Non-square numbers, non-perfect squares are also included in that. Wait, let's just see. No, we Google. So the cubes, set of perfect cubes, right? It's just like squares, set of cubes. 1 cubed is 1, and then 8, and then 27, and 64, and 125. Which one has more elements? Which one has more elements? N, right? Because in addition to cubes, N has those squares that are not cubes, and it has many other things, right? So a number can be both cubes and square also. Like 64 is cube also, and it's square of 8, and it's also the cube of 4, right? It's the cube of 4, I guess. 4 into 4 is 16, into 4 is 64. Yes, okay. So C seems to be significantly smaller than N, right? This set C cubes. X, the set of powers of 2. Powers of 2 are even sparser, right? So like I told you, in terms of cubes, in terms of squares, when I reached from 1 to 100, I skipped 90 of them and selected only 10 out of them, right? In this case, I will reach 1024 and only select 10 numbers and skip all the remaining 1014 numbers, right? Or in 10 steps, I went to all the way up to 1024, right? So in 30 steps, I will reach 2 billion, 4 billion, okay, 1 billion. Okay, so X is strict subset of N, and seems that N is much bigger than X, right? This is the definition of finite sets. For finite sets, the theorem that the cardinality of 2 sets are equal if and only if one can establish a bijection between them, right? This is what Cantor defined kind of the cardinalities of infinite sets, or the cardinality, the equivalence between cardinalities of infinite sets, right? All he did was just erase the word finite from that. He said, Okay, if for any two sets, the cardinalities are equal if and only if there is a bijection between f of x and there is a bijection between x and y. Okay, if with this view, so now I just defined when two cardinalities are equal, right? So let's see now again those two things. It means that if x and y can be placed in a one-to-one correspondence, if there can be a bijection between them, meaning they can be placed on top of each other such that it's a one-to-one correspondence, everybody has one below it and everybody has exactly one unique above it, right, in this this two-dimensional listing. So then if there is can be this one-to-one correspondence, if I can do this, establish this counterpart relations between them, then the cardinalities are equal, right? So let's see this thing: z plus positive integer, z minus negative integers, positive negative integer, no sorry, negative integers, all of them, we thought they were equal, right? Why did we think they were equal? Because they looked equal, right? So there is a negative number, and for every negative there is positive, for every positive there is negative, right? And that's the correspondence we established. That's why we thought it was equal, right? So but the Cantor's definition of equality of these two things would require a bijection between them, right? So that's going to be your, so if I look at these numbers like this, right, in our brain, when we made the statement, when we thought that the cardinality of z plus is equal to the cardinality of z minus, we were thinking of this. Okay, this actually gives us this bijection, right? So give me that bijection, write it informally, formally. What is the bijection from z plus to z minus? Quickly. What is the bijection? What is f of 10? What should be f of 10? I mean, it's your choice. Okay, you can do whatever you want, but give me one, the more natural one, or the one that I drew it here on the board. F of 10 equals negative 10, right? If you do that, that should be a bijection. Is it a bijection? Can it happen that negative 10 is not mapped to anything? Can any number negative I not map to anything? Where is negative I mapped to? I, right? By that bijection. Could it happen that some I, f of I and f of j is equal? No, because f of I is negative I and f of j is equal to negative j. That's a bijection, and this is a bijection. This function is a bijection. Hence, these two are equal by the Cantor's definition or Cantor's characterization of equal cardinalities. Okay. So we conclude that the cardinality of z plus is equal to the cardinality of z minus. Now look at this, the set of odd numbers and even numbers, we also thought they were equal, right? They had equal amount of actually equal mass, they have equal number cardinality. Why is that? Where is the Cantor's definition for that? Huh? If I map every number I to I plus 1, then f of, these are positive odd even integer, okay? So 1 is mapped to 2 and 2 is mapped to 3 and 3 is mapped to 4, but you see this thing, you see exactly, here is in the picture you should see this. Look this from 1 to 17 and these numbers from 1 to 17, exactly the same number appears here, right? That's the correspondence between them. And what is, you write this correspondence, well I told you f of x equals x plus 1, this correspondence establishes that the cardinality of this set O is equal to the cardinality of this set E. Okay. Okay. Here are the other one that are more, which is more counterintuitive. Here is a set of natural numbers, set of even numbers. We know that the set E is a subset of the set N, right? There seems to be more natural number than even numbers, but Cantor says that if you could establish a cardinality, if you can establish a bijection between them, then there must be equal, right? So look at it like this. That's how we look at it, and we seems like, you see, the set E is missing every other row of the first list, right? The first column, right? Every other element of the first column. But if I look at it like this, right? So there is even numbers, but I can talk about even numbers like this. There is the first even number, then the second even number, then the third even number, then the 19th even number, then the 1944th million number, and so on. Even number, right? It's clear? So, can you write this bijection? What is the bijection? F of x is equal to 2 times x, right? Every natural number is mapped to its double. Is it a bijection? Is f of x equals 2x a bijection?
Yeah.
If you remember, at some point we discussed exactly this function and we said it was not a bijection, but that was f, the domain and codomain was defined to be integers, right? In that case it isn't, right? On one side they are all integers, on the other side, but here the domain is z and n, and the codomain is e instead of even numbers. Yes?
Cardinality of n must be equal to cardinality of e.
No, that's what we get. When we get the bijection, then the cardinality becomes equal. We want to verify, we want to prove that the cardinalities are equal. Cantor said cardinality will be equal if and only if you have a bijection between them. So, I just have to show a bijection, right. So, this is what is the bijection here? Where will be, what will be f of x? 2x, right? And this, you see this, look at, do you see now in this picture, it's not very easy to see that. Can you guys please stop talking? In this picture, it's not very easy to see that they have equal number, right? The equal cardinality. But if you look at it like this, then it's quite easy to see that they have equal number of elements, right? And that's where the bijection thing is coming from. So, it's like a more pictorial way of visualizing the Cantor's definition. Okay, set of natural numbers, set of squares, very few, very sparse set of, compared to n, set of squares is very sparse, right? You see how many elements are missing from S that are already there in n. Yes, they are there, they are number that are there in n, but they are missing from n. Is 5 here in S? Is 17 here? Is 19 there? Right? Many numbers are missing there. But if I look at it like this, look at this, if I look at it like this, then do you see is there anything missing? And numbers are still missing, but it doesn't give kind of room for this, right? There is 17, then but there is 17 square. There is 1842, then there is square of 1842, right? And all for each one, for each natural number, I have a square. For each square, I have a natural number, right? And that's the bijection between them, right? What is the bijection here?
F of x is equal to x.
Can you give me a bijection from S to N? Yeah, f of s will be f of x number x will be the square root of x in a natural number, right? Now, because the perfect square, its square root must be the positive square root of x. Okay, so there are two. Square root is not technically speaking a function because it maps x to the negative square root and the positive square root. Okay, and it's okay. So the bijection is f of x equals x squared. The inverse of it, which will also be a bijection, is actually f of y equals the square root of y. Okay, so here is that bijection. And similarly, you can see for the sum of cubes, how would you look at it? You would look at it as 1 cube, 2 cube, 3 cube, right? So for each number, I have a cube, and for each cube, I have its cube root as a corresponding integer. Are you TA? No, you are TA. You are not TA. Okay. Okay. So, okay. So what will be the correspondence? What will be the one-to-one correspondence between this set of natural number and set of cubes? Every number is mapped to its cube, right? Or every cube is mapped to its cube root, right? Bijection is a kind of a both direction thing. Okay. Similarly, set of squares. See very few numbers here on the right in the right column, right? But there is 17, there is the 2 raised to power 17, there is 18, and there is 2 raised to power 18. So if I look at it like this seems exactly equal amount of density in the both sets, right? And that is, yes.
So does that mean every two infinite sets have
That's a good question, we'll see in a minute. Okay, that will be our next question. So, okay, these infinite sets have the same cardinalities as n. So far on one side we mostly had n, but we'll see. Okay, so f of x equals 2 to the x is the bijection. What is the bijection from x to n? Give me a bijection from x to n. G of y is equal to log base 2 of x y, right? Log base 2 of y, that's the inverse function, that's why. Okay. So, Cantor wrote in a letter to Dedekand, those of you who work in real analysis will hear the word Dedekand, Dedekand cuts and other stuff. Cantor wrote to Dedekand that I see it, he just defined it or he just worked without it, but I just don't believe it. What does it tell you? We know there are half as many even numbers as natural number, right? Half as many positive even number as natural numbers. It makes sense? Because 1 is not there, 3 is not there, I am skipping every other, I am collecting every other positive integer to make the set E, the set of even numbers, positive even numbers, and I am taking all the natural numbers, and then we conclude that they both have the same number, right? So, it basically tells us that size divided by 2 is equal to size, right? The natural numbers, even if you half it, you still get the same number as the number of natural number. That is how infinite sets behave. Okay? So, I see it, but I do not believe it was the statement he made it. So, this notion of cardinality actually enabled us. Now, we can say statements like this. Oh, what if I add one more element to an infinite set? What happens to its cardinality? Does it increase? Does it decrease? What happens? Yes. और अगर ना जाऊँ तो sorry, please repeat.
How do we then conclude that they are more irrationals than rationals?
That's a good question. So we'll come to it in a minute. So we'll right now so that is our next thing. Good question, right? That's what we see. We never concluded anything, right? I have never made any such claim in this course so far. Okay, only claims I made is what I proved, because you still live in a world where 2 is equal to 1. Okay, so do you see this? What if I double an infinite set? What if I replicate every element of a infinite set? What will happen to its cardinality? Will it increase? It will stay exactly the same, right? That's what happens. So, even numbers, even if I double it, I get all natural numbers cardinality which is equal to this thing, right? What if I divide it by 10? What if I take the square roots of that cardinality? Still this cardinality. So, all of these things, these are not arithmetic formula. This equality is not really the arithmetic equality. This is that cardinality between infinite numbers, infinite cardinalities, infinite sets behave like this, okay, in terms of their cardinality. So, now we are going to come to your questions, and I was not going to cover it, but you asked the questions. Let us do it. So, this is all our thing, right? It will also answer your hastiness. We define a set to be countable if it is either, please, this is important, okay? A set is called countable if it is either finite. So, all finite sets are countable, but if it is infinite, it could still be countable. An infinite set is countable if it has the same cardinality as a natural number. Okay, when I say equal cardinality, now I know it. And what does it mean when a set has equal cardinality as a natural number? If there exists a bijection between that set and the natural number, right? Okay, so a set is called countable if it is either finite or it has the same cardinality as natural numbers, right? And just replace with the same cardinality with the other side of equivalence, the if and only if it has a bijection with the natural number. If it can be placed, if the elements of that set S can be placed in a one-to-one correspondence with the set N, right? And now you just think about it. Remember how we defined sequences. Sequences is a set or a multi-set where some order is imposed upon them, right? So essentially an ordered multi-set. And there was, I said, okay, there is a function that gives from natural number to the set elements, the elements of a set S. You are getting all the hints for the long quiz too, because sequences are part of that, right? And also functions are part of that, right? But so this was a good timing for those things. Thank you. So